Welcome to lecture 6th of the course on corrosion, environmental degradation and surface engineering. Topic of this lecture is fatigue, melting and diffusive wear mechanisms of surface degradation. Diffusive wear mechanism will be introduced in this topic. However, we will detail this topic or this mechanism in 11th lecture. So, question comes first, how so many topics have been covered in this lecture. Now, if you remember, in lecture 1 we presented one slide about the material degradation mechanism or surface degradation mechanisms, and we say in mechanical action we will be covering the wear and we will be covering the fracture. So, we are trying to complete this topic wear in today's lecture or in the present topic. Fatigue wear we will be covering, fatigue wear we will be covering, fatigue wear, melting and diffusive. As I mentioned, the diffusive wear model will be just introduced in this topic and then we will detail in lecture 11th. So, what will be covered in the 7th lecture? It will be covered a fracture or mechanical fracture mechanisms related to mechanical fracture. In lecture 8 we will be covering about the heat and radiation actions causing the surface degradation. In lecture 9 and 10 we will be covering the chemical action or surface degradation due to chemical action, and 11th lecture we will try to cover correlation or maybe say relation of various mechanisms. So, that is why the diffusive wear mechanism is more suitable there, it will be always associated with some other mechanism. So, we will cover in detail diffusive wear mechanism in 11th lecture. Now, start with the fatigue. As I mentioned, fatigue, melting and diffusive wear, and why we are covering all the 4 topic in one lecture. One was that we will be covering the complete, we will want to complete the wear mechanism topic. And another point which is important point is that these mechanism they coexist or they add within one or another mechanism. Sometimes fatigue helps fatigue corrosion and the fatigue mechanism, sometimes fatigue finally comes to the melting, and then addition and diffusive are connected as wear coefficient in more or less all mechanism will be much lesser than 10⁻⁻⁷. That means indirectly or directly fatigue phenomena is going to happen on those wear mechanisms. So, it is really required to cover all these 4 topic in one lecture. Now, what is a fatigue? I am assuming that everybody has a knowledge of the fatigue. What we say, the fatigue is resulted because of the cyclic loading or repeated loading. In this kind of mechanism, every material will experience alternating or maybe say variation in stresses as well as a strain, and then finally this kind of the loading will cause a crack formation and crack enhancement. Product will finally fail if the cracks are many and bigger in size and completely pit formation or many pits are formed there. So, what we can say in the complete mechanism, the fatigue crack or initial one crack will be a starting point not only in fatigue, but is also many times starting point in the fatigue mechanism or fatigue wear, and it is also many times a starting point in the melting wear. Coming to fatigue, we say it is a form of abrasion. So, again there is a relation, because particle will be formed and then, but the particles will remain in localized domain and particles will cause more wear. That is why we are using the 3 body abrasion mechanism is very closely related to fatigue. And then we are also mentioning in the fatigue will occur when there is a oscillatory motion, which will cause a dynamic loading one way or another way. However, what is the difference between the fatigue and fretic? We are talking about something like a very small amplitude, even a tune of 1 micron. So, that is why the special case of fretic question comes, how that small movement is going to cause big failure. We will cover those things. So, that is why we say the localized surface degradation from fretic may include material loss. Material will be lost, but intact at the one place. As you open a connection, you will find a lot of debris coming out that. It will cause some sort of pitting also there. And another thing, accumulation of the wear debris in one location, a lot of energy to compress that also. So, these are the related phenomena connected to one way or another way to the fatigue loading. So, that is why the many times people use a fatigue wear or fatigue wear. This you can find in a Google search, this kind of a topic people have mentioned, or maybe say they have described also. Now, what are the important aspects? Stress concentration is important, which is causing the fatigue wear as well as the fatigue wear, and as I mentioned, they are related to each other. Loading will be oscillatory or some sort of dynamic loading will be there. There will be fluctuation in load or torque or on the speed of its oscillatory motion, and that is why the fatigue wear will occur. This is a special case of melting, and we keep melting wear in a very severe wear domain. If you remember in earlier lecture, we focus on ultra mild wear. We should design product with a keeping in mind that ultra wear mode should happen, but melting wear is a severe wear. That is why we need to really think about this. And another thing, not necessarily melting wear will occur immediately, it may take a number of cycles also. So, we need to keep monitoring, and then we should be able to predict well in advance this kind of wear. And in this case, basically as the melting word is coming, naturally we will need to think about the temperature. If the temperature or working temperature or the temperature at the contact point is greater than melting point, naturally localized melting will occur. And if localized melting will occur, the metal or solid will be getting converted to the liquid or maybe this is semi-solid. Why this kind of temperature occurs? Sometime environmental condition or the high temperature condition, so it can come directly from environment. Second thing is the frictional heat, that means the coefficient of friction is higher, and then body is not able to dissipate the heat. There is no sufficient cooling to reduce the temperature, and temperature gets accumulated over the time and finally it reaches to the melting point of material or the surfaces. That is why when the melting occurs, that is why we have written also hot surfaces, they are unable to dissipate the heat, and material suffers a loss of volume. Not only the loss of the volume, but microstructure change will also occur. That means whatever our design intent will fail by completely. Microstructure will change, material properties will change, and then behavior will be different. So, we should avoid this kind of wear. We should design a product in a manner, we should select the material in a manner that this melting wear should not occur at all. So, that we need to give a lot of emphasis on that. Coming to the diffusive wear, we have already discussed this kind of wear mechanism in adhesive wear. We say in adhesive wear, metal are more chemically active, they transfer the electron from one metal to other metal. Even the metal can transfer electron to the non-metal, but reactive metal, reactive non-metal. So, this is a very important. However, in this case additional parameter is coming, or maybe the additional variable is coming, that is a high temperature. Diffusive wear will not occur the low temperature, and diffusive wear is a slow process. It does not happen immediately, instantaneously the way adhesive wear occurs. So, in this case temperature is important, and then as temperature is going to play a role, quite possible it may get added with a melting wear, or there is no sufficient diffusion of energy, or no cooling agent, or no lubrication, that may be causing the diffusive wear. And this is one of the very common phenomena in the tool wear mechanism, where the diffusive wear will occur, and then the tool is losing some sort of material to the chips, which will be finally rejected. So, no use as such, but tool wear will be occurring, and we need to prevent that. Now, coming to the, as I mentioned earlier, the why we are covering all 4 topic in on the one lecture, we say all 4 phenomena are connected and influence each other. So, there is a dependence, they will be affecting each other. Now, how they are depending on each other, I am just trying to explain it. See, the lack of heat dissipation, it will also cause a cracks, and that will also result in the fatigue, because once a crack is initiated, fatigue will enhance it, fatigue will enhance it, and then finally, there is a possibility, if the temperature is increasing, quite possible the melting will also occur. Another mention, the fatigue has a potential for the localized melting, because a lot of wear particles will coming out during the fatigue phenomena and may increase abrasion, and then there is no heat dissipation mechanism available. So, localized heating or localized melting is possible there. And coming to the fatigue, also it is a possible as a relation with a frictional heating. So, it appears that more or less these parameters or these wear mechanisms are connected with each other. Also, we say that melting is maybe directly or indirectly related to frictional heat. So, if any cause, any response due to increase of frictional heating is related to melting. If any material is getting weak, stresses are increasing significantly, or the load is increasing significantly, it is generating more number of particles, and the frictional heating is generated enhanced significantly, then they are related to each other. Now, finally comes diffusive wear. In this case, as we know that if there is a lot of frictional heat, temperature will increase. If the temperature increases, diffusion wear will increase. Now, this temperature increase has maybe because of the lack of dissipation, and then there is a chance of the melting wear and a diffusive wear almost the same time, or maybe the fatigue is slowly making the component weak and accumulating a lot of particles and increasing the coefficient of friction there. So, they are related to each other, and that is why we are covering in this topic. Now, let us start with the fatigue wear. It is one of the very common wear. As I say that coefficient of wear coefficient, if it is lesser than 10⁻⁻a or 6 to 7, maybe say 7 is right thing, then the one way or another way all the wear mechanism are involving the fatigue wear. So, it is one of the very important mechanism. We know that particle will get removed from a surface, and there will be some probability, and that is represented by the wear coefficient. If wear coefficient is lesser than 0.7, that means there will be repetition of the cycle at least 10⁻⁷ times, then only the wear will occur, and indirectly the fatigue is related to that. Now, what we can elaborate, the fatigue wear will occur as of the periodic loading and unloading. Reversal of the cycles will be there, and stress will be going to positive to negative, or positive to 0, or negative to 0. That is why we say this failure is attributed to multiple reversal of the contact stress, and this is also indicated the wear coefficient lesser than 10⁻⁷, or the probability of failure is say once in a 10 million, then fatigue is really happening there. This has already been mentioned, repetitive stress, but we know very well this stress need to be much lesser than ultimate strength, or even the what we many times use endurance strength of the material. Another important point which we have seen, that there will be some sort of a crack formation or some rupture formation at the material surface. It is a localized phenomena. Now, this localized phenomena is happening maybe because of the high heat, maybe because of the fatigue, or maybe happening because of the there is a repeated loading, and maybe some particle is getting trapped there, maybe abrasion. So, there is a possibility. So, whenever there is a small rupture start on the surface, then because of the fatigue, that rupture will progressively increase in its size. Even depth will increase, length will increase also, and that is what we are saying, expand progressively under cyclic loading, eventually leading to material failure or surface degradation. We also know that sometimes crack forms a few micron or few micrometer below the surface, maybe even we can say 100 micron below the surface, where there will be high shear stress. Why there will be high shear stress, we will be covering in the next few slides. And then another important thing is that if the crack is a perpendicular to the load direction, or maybe the maximal tensile stress, then opening of the crack will be much faster, and then failure will be also much faster. So, depends on the crack location and orientation also. So, that is why these are the facts already known. Fatigue wear related to phenomena. We are just repeating those things. Now, another points come, is it anywhere related to Orchard equation, and I mentioned about constant or coefficient of friction or friction coefficient, sorry in this case wear coefficient. It is related, we say fatigue wear leads to permanent deformation, it may be plastic deformation, formation of crack that will grow and form a wear debris, and if the wear debris is coming out of the surface, one form to represent that is a Orchard equation. So, even Orchard equation in dry lubrication case can be used for this purpose, and many authors have invented or written many more mechanism or more equations, but Orchard equation is one of the very simple and getting adjusted to almost all the mechanism. Only thing will be one important parameter, that is a wear coefficient will be unknown. We need to do number of experiment to find out wear coefficient. If we are able to find out, then even we can develop a mathematical model to predict the fatigue wear well in advance. Now, fatigue wear is a common phenomena in the rolling bearings, in a gear. These are all of the rolling elements. The gear also rotate, power transmission happens, frictional drives, cams and followers. If you find everywhere comes some sort of contact stress will be very high. That means indirectly wherever there is a high contact stress and some sort of friction or tangential motion, fatigue is bound to happen there. We can say here, even in every case, in almost every case, every surface will have some sort of asperity, and bending of asperity or tearing of asperity or crack formation of the asperity will occur if there is a relative sliding. That means, this localized fatigue will occur in almost all the cases. There is not a single case where localized fatigue will not occur, and this is important for us. So, what we can say, fatigue plays a significant role in abrasive and adhesive wear mechanisms also. Reason being asperity. Asperity is going to get loaded and unload continuously, and that is a fatigue phenomena or local fatigue phenomena, and that is why we say the abrasive wear and adhesive wear are related, or maybe we can say the fatigue plays any starting step towards the abrasive wear or adhesive wear. Let us start with the fatigue because we divide fatigue into two ways. We say fatigue wear during rolling will be somewhat different than fatigue wear during sliding. What is the slide to roll ratio? So, here we are assuming the perfect rolling, or majority of the rolling motion occurs, a high amount of the energy is going in the rolling action only. And I have shown in one figure there are number of pits. You can see this is a complete density of the pits, there is a complete density of pits, or maybe say several pits are there. That means one pit formation does not cause a failure or fatigue failure. There will be a continuous, obviously the several number of pits will be there. However, we know very well progress will be much faster. Maybe x time is taken to make a one pit, quite possible 10 pits will be formed within a 2x time duration. So, the progression will be much faster, progress will be much faster. And this is a outer ring of roller bearing, which I analyzed in maybe say around 20 years back, and this is a perfect surface fatigue, no uncommon failure, it is a very common failure, and this bearing could survive more than 40,000 hours of operation, right. So, this is the operating hours for more than 40,000 hours. So, this is a perfect bearing, this kind of a failure will occur, and this is a fatigue phenomena after 40,000 hours. Either we can inspect or we can simply replace. If we inspect and we find the bearing is in a good shape, we can recondition or we can reutilize it and then maybe increase slightly more maintenance, because this bearing itself was costing around 35 lakh rupees. So, this is important to understand the mechanism, what is a normal fatigue wear and what is a sudden fatigue wear, which will cause a fracture, which we will be covering in the next lecture. Now, if you want a perfect and reliable bearing, so what we require, we say rolling bearing requires a smooth undamaged contacting surface to start and perform reliably. That means, this bearing cannot now work as a reliably, reason being there are number of several pits are available. Then what will happen, because of so many pits, we say that pitted rolling surfaces prevent a bearing from being used due to severe vibration, because there will be lot of irregular surfaces, and then they will be causing the irregular vibration also, and then bearing cannot sustain it, maybe the loads unnecessary will increase, and if you do not stop here, it will lead to the fracture. And we can say here bearing can survive reliably if whatever the number of cycle we have designed, it is able to sustain before showing noticeable number of pits, and here the naked eye we are able to examine. But as I mentioned earlier that lesser than 50 micron we cannot see even the pit of any size. So, if the pits are many and then we are not able to see on the surface, and that we can say we can continue, we can operate that bearing. Now, question comes, how and why this many number of pits emerge on the bearing inner surface, or maybe say outer ring of the rolling element bearing, and this is the inner surface of outer ring. What are the steps? We say that first step is the application of a normal load that induce high stress at the contact point, and in this case what we are talking about, the high stress is something like greater than 2 gigapascal. The stress level goes to such a high value that more than 2 gigapascal. Naturally, under such a high contact stress, what will happen? There will be plastic deformation, but plastic deformation is very low and noticeable, and we say that plastic deformation is much lesser than overall dimension of the bearing. So, that is why it is not really worrisome that much, and that what we are talking per cycle. As the number of cycle increases, the deformation will continuously increase. If there is a continuous increase in the plastic deformation, then there is a possibility of some sort of a crack nucleation. If there is some sort of material defect, or maybe there is very high coefficient of friction, even the surface will show the crack if it is a perfect and coefficient of friction is also under control, then there is a possibility subsurface crack formation occurs or nucleation will occur just below the surface, and that has been shown initially dynamic loading or fatigue loading on a surface, because the stage B, this is what we are showing the stage B, number of cracks maybe say initially only one crack, then second crack, third crack, fourth crack, something, density of the crack is increasing. Quite possible in third we see the expansion of crack, either maybe initially this crack was a smaller size, now it gets aligned or it becomes a perpendicular to tensile stress, then it will get expand. So, there is expansion of crack due to reversal of the stress, and extension of the crack to the surface possibility is here, and slowly it will move also towards the surface. There is a possibility that this crack will get extended to the surface, and quite possible it is the coefficient of friction is increasing that time, and that is why we are writing that because of the traction force. Finally, it will come out as a wear debris, and this wear debris even can be 10 micron or maybe the lesser than 10 micron in size, effective size. It can be lesser than 20 micron, which will not be noticed to us with the naked eyes, and such a big bearing you cannot really use a SCM or other microscope immediately to find out the failures are occurring. So, we need to believe on the time scale or many number of cycle it has executed, and then we need to inspect according to that. So, in this case suppose there are 40,000 hours operating life, will be quite possible after every 1000 hours or wherever there is a routine maintenance, we can observe whether the cracks are formed or pits have been formed on the surface or not. So, these are the important aspects or the important mechanisms with the fatigue wear is important, and it may lead to the failure of the component, we need to keep observing it. Now, let us start with the fatigue wear during sliding. In previous slide we say rolling, we given more emphasis on the rolling. Now, we are going to give more emphasis on sliding. We prefer always rolling motion, we do not prefer the sliding motion. Reason being, in sliding coefficient of friction increases, and in rolling coefficient of friction decreases or maybe the lesser, and in the rolling it can really sustain very high contact stress. So, in this diagram what we are showing under the sliding, may I assume that this is the sliding direction. You can see the top layer which is highly deformed, we are not able to see the grain orientation, it has moved completely in parallel to the sliding direction itself, and this thickness can be even a tune of 100 micron or maybe say 0.1 mm. This is completely deformed. So, this is what we say friction affect the thickness T. If the coefficient of friction is near unity almost 1, many people do not believe that coefficient of friction is more than 1, there is a possibility, but we have seen coefficient of friction much more than 1 also. So, coefficient of friction on a higher side even the 0.9, 0.8 or maybe say 1, then possibility that this complete layer the T has been shown that it will deform in the direction of the sliding, and that is what we are using, that is why we want to study the fatigue wear during sliding. And another has been mentioned that we have shown a number of we say that divisions, this is the division 1, this is the division 2 and maybe division 3. Then the division 2 we are able to see dislocation of the cells, and we are using the word moderately deformed surface, and that is causing some sort of void formation, nucleus formation in this. So, that is why this figure it shows sliding induced surface stresses. We have discussed about the thickness T. We say under extreme sliding condition where the coefficient of friction is almost equal to 1 is a significantly higher, and then this complete layer, that the dark layer will be deformed in the direction of sliding. And then if there is a lesser friction or maybe lubrication has been provided, then this deformation may be reduced, this thickness will be reduced also. And then as a deformation is not happening that much and sliding is not going to impact that much. So, it will give a overall good results. So, sometimes we say that if you want to minimize, you want to reduce a fatigue wear during the sliding, provide a good lubricant. So, coefficient of friction comes down significantly. We talk something like a coefficient of friction even lesser than 0.1. So, here we were thinking about equal to 1 and here we are saying the lesser than 1 or lesser than 0.1. So, this is the important. Otherwise, maximum shear stress will occur at the surface if they are under high stress under high sliding and coefficient of friction on a higher side. And then in this case what will happen that the surface grain structure will somewhat collapse and create a dislocation, and that has been shown over here. In this area there will be possibility of the dislocation cells or the dislocation of cells and then formation of voids, formation of cracks in this formation. That means, if there is a crack formation there will be possibility here that in this number 2 there will be possibility of the void formation and crack nucleation. Now, third layer, which is what we are using, the material with inclusion. If there are inclusions, as such fatigue is not going to create much problem for the third layer or the third this region as such. But if there are inclusions or maybe time we use some sort of alloys, we try to give some high thermal conductivity, some sort of nanoparticles we mix, but that will also give a possibility or increase the possibility of the fatigue wear or initiation of the cracks. That is what we are writing. Most engineering materials have inclusions or the defect that cause voids during the plastic deformation. Under loading and unloading, there is a possibility the void forms. In this case, there is some crack here, some sort of a discontinuity here, some sort of a foreign element, or maybe say that inclusion is there. Then in this situation, it is going to really form the nucleus, and in this situation quite possible it will act like a brittle material. Finally, whole chunk may come out as such. So, there is also possibility. That is why we say as far as possible in case of the fatigue where the sliding is included, we should use inclusive free material, that will give better results. And typical example which has been quoted is a pure copper. Pure copper which does not have much inclusion, it has a high coefficient of friction, but very low wear, and that is why we say that it is important for us to consider. Often people feel that a high coefficient of friction means high wear rate, low coefficient of friction means a low wear rate. It is not really synonymous or they are not directly related. There are number of situations, higher coefficient of friction will give a lesser wear, and lesser wear and maybe say a low coefficient of friction may provide a high wear. So, they are related to each other, we will be covering those things also. So, what we have covered in the previous slides, we say that there is a tendency of the different material to generate a dislocation cell, and that varies will depend on the material to material. What is the reason for that? Generally we use the word stacking fault energy. If the stacking fault energy is there, it will increase the cell formation. Let us take an example, as I say, the iron, copper, aluminum, they produce a dislocation cell due to their large stacking fault energies. The cells are relatively thin, elongated in a direction of sliding at the interface, and may be acting like a flight tiles. If the flight tiles will act show some sort of a possibility of the dislocation and causing a more and more chances of the fatigue wear. However, as a given an earlier example of the pure copper, this is we say that when the inclusions are lesser, it will show the better results in the wear. However, if the fault energy is on a higher side, then it will not show that much. And another thing is that location where the void formation and the crack nucleations are likely to occur are the energy specific. If there is a high energy cells, then it will really give a more and more voids. So, again they are related the way we have studied about the addition. If there is a more energy, there is a high energy, there is a more chances of adhesive wear. Similar thing happens to the fatigue wear. If there are high energy cells, and that it will cause a more and more chances of the void formation or crack formation. And then it will cause the wear which not necessarily immediately occurring on the surface, and it may cause us below the surface also, because there is already some sort of a distorted cells are available, and that may cause us some sort of a problems. And sometimes we can say the fracture which is related to fatigue will start at some weak spot, wherever the weak spot. And now when we say the crack, there is a weak spot. If there is a grain which is having a kind of very high energy, that is a weak spot, and then it will start at the fracture, they start from that location and slowly will spread, and finally it will come to the surface, that will be causing the fatigue failure in a bigger way. And sometimes we can say that there is a secondary cracks much deeper available, but continuously plastic deformation, or maybe say continuously loading and unloading, and this will cause more and more crack formation, and then they eventually they get together, they join together, they they will move toward the surface, and then the failure of the surface will occur, degradation of the surface will occur. So, fatigue has been very simple, it has been studied extensively, and we say as far as possible, if surface energy is lesser, cracks are lesser, then we will not have a much problem, but discontinuities is more, possibility of surface dislocation or maybe say voids are more, than the fatigue wear will occur. Let us take some example of the fatigue during the sliding itself. I want to just demonstrate what will be the mechanism. So, this is what I am trying to show, and particularly it has happened in the gear, where we are experimenting the gear under sliding condition, because we do a rolling, but there will be some sort of sliding formation will occur, sliding will occur on the gear surface. So, I am just showing here that the reciprocating motion of the surface 1, this is the surface 1, this is the surface 2, I am assuming there is some sort of a crack on the surface. Now, if I magnify this, surface, we are able to say there is already surface initiation, and then if we continuously reciprocate, there is a possibility the crack also propagates in the similar manner, and if there is a crack is propagating in a similar manner, finally it will lead to this manner, and then the complete chunk will come out, and that is a very dangerous, particularly for sliding wear. We know that orientation because of the sliding, that the crack will get oriented towards the sliding direction, and then whole chunk will be removed from a surface, debris will come out, and that is a problem. Now, this is what exactly I was mentioning, that if there is a lesser and lesser inclusions, lesser and lesser possibility of cracks, lesser and lesser defects, then the fatigue will not create a more problem, otherwise there will be some sort of initiation of the crack, and it will propagate, and finally failure will occur. So, what we are writing here is a surface initiated crack expand during unlubricated case. Again, if I provide a sufficient lubricant here, then the coefficient of friction will decrease significantly, dislocation of the top surface which is getting parallel immediately to the sliding direction will not happen, and then even crack will reduce, or maybe the whatever the initial size of the crack may remain for the many cycles similar size, it will not enhance. So, in case of unlubricated sliding, there is a possibility of wear particle formation, and then under lubricated condition quite possible wear particles may not come. And sometimes we say that wear coefficient under we say that lubricated case is far below than a unlubricated case. So, we need to think from wear coefficient point of view, and if you want a very low value of the wear coefficient, provide some sort of lubricant. Now, a lubricant can be in form of the oxide, lubricant can be in form of the solid lubricant also, or lubricant indirectly can be in form of the coating which also acts as the lubricant. So, we need to design the surfaces to enhance life service life or longevity of surfaces. And this is the example which I wanted to I was mentioning about the pure copper is something like a 99.96% pure copper generally the even common copper will have some sort of inclusions. If this 99.96% copper which one of the author has done experiment, see it slides against a steel. In this situation it has a wear 10 times lower than any other material. If you take any other material and slide that material against a steel, that will have a much higher wear rate compared to the pure copper. However, coefficient of friction is on the highest side. That means steel and copper, the pure copper coefficient of friction will be very, very high, but wear rate will be low, and that is what I will say, high coefficient of friction but low wear rate. So, this is not a velocity, it is a wear rate. And now another example, we say carbide rich steel, which will provide a low coefficient of friction, but it will give a high wear rate because it has a number of inclusive, and then those elements are added to increase hardness value of the steel. So, coefficient of friction can be reduced, but they also experience a high coefficient of friction. So, in short, there is a possibility of giving this kind of pair, low coefficient of friction but high wear rate. Again I say this V is not a velocity, it is a wear rate. Now, we are understanding the wear mechanism, and then we can design product, we can design surfaces which can really provide a much better life, much longer life, and then overall give a good results to us. So, this was the fatigue wear, and now let us may summarize the fatigue wear combined manner. What we discussed, something like a fatigue wear sliding direction, and then we say the coefficient of friction. Coefficient of friction in this case is suppose very high, then what will happen, that this shear stress, maximum shear stress location will shift slowly up. If the coefficient of friction is more and more, maybe say mu 1 is more than mu 2, and mu 2 is the like kind of lubricated condition, mu 1 is unlubricated condition. That means unlubricated condition, location of the maximum shear will straight shift up and maybe even slightly on a higher side, while lubricated conditions or maybe in some other cases that the shear stress will be below the surface. And we know that contact stress will be very, very high in this case of the fatigue. So, it is subjected to both compressive stress and in tangential motion the tensile stress, and we can quote now, we say if coefficient of friction is lower, maximum shear stress just occurs just beneath the contact surface, just beneath maybe even 100 micron, 150 micron, 200 micron, just beneath does not mean 0.1 micron, it is on the 100 micron plus. Then what will happen, and then the contact stress are very high at the interface. In the situation under repeated rolling and sliding contact condition, fatigue wear mechanism involve the propagation of subsurface cracks. If there is a surface crack also, that will propagate, but suppose the surface is perfect and there are only the subsurface cracks either initiated because of the sliding and the repeated loading, or there were some sort of inclusions, or there were some sort of voids already, and that will get propagated, and finally it will come to the surface as a particle or wear debris particle. So, this is related to that, and this case has been always obtained on the observed in case of the gear. Pure rolling occurs only on the pitch line. Above pitch line and below pitch line we find a sliding occurs, and because of the sliding and rolling and the very high contact stress, whatever has been written here it will be there. So, what we can say, combination of the sliding and rolling condition puts the top surface layer of the gear tooth under tremendous strain. So, maybe if I say this top surface of the gear, it will be subjected to under very high strain, and under high strains, these strains under these layers are vulnerable to the cracking, because under very, very high strain they are subjected to the cracking, and that cracks formation will occur, and which will finally or eventually lead to the wear particle generation. Now, coming to the real the gear wear which we have observed in the lab is something like this. What we use a pitting wear and you can see there are number of pits on the surface, or even many times wear particles they get embedded in this also. There is a possibility. Wear particles which have been generated, they are under load, under high contact stress, they get embedded, and once the particles get embedded, it will give indirectly high surface roughness, and that will lead to the abrasion mechanism. So, fatigue may lead to the abrasive wear or severe wear in this situation. So, we can say here the applied stress and the number of cycle, material characteristics and environment. Many times even and the presence of moisture will allow surface to get corroded, because whenever there is oxide layer is removed from a surface under the high friction, the nascent surface will be exposed, or pure surface will be exposed which has a high energy, and that immediately that will get and then react with the water, make another oxide form, and then that is what we call the corrosion may occur, which may be higher side compared to the normal oxide wear. So, this is the environment also plays important role, and all these parameter will affect the surface failure or surface fatigue. So, these are the important thing. What is the stress level, how many cycle, material properties, whether the brittle or whether it is the brittle or maybe say ductile material, and environment, what are the elements in the environment, and then if they are chemically active which can react with the surface, then corrosion assisted wear will also occur. Now, coming to the second topic which why we use the word the phatic wear. It was this term came in somewhere 1927, and we have observed this is a very silent killer. Phatic wear is a silent killer, it does not give any information, and whole structure will collapse in a short span of time. Again, it will experience a number of cycles, but it will not give a visible sign. In case of the pitting, at least it will show some pits, and during regular maintenance we can identify it. And then in the phatic, because many times it is a happening into the interference fit. Interference fit generally we do not open even during the routine maintenance, and that is why that there will be major problem. Now, coming to this phatic wear, as I say, it was introduced in 1927, and then we say the motion will be occurring in a somewhere range 1 to 300 micron, but the motion will be high frequency motion or oscillatory movement. Often it is getting subjected to vibration. You assume there is some sort of a pair which is interference to fit, and you load in one local place. After 1000 kilometer of the travel in the truck, it must have experienced many cycles of the low amplitude high frequency vibrations, and that may cause some sort of failure, some sort of the pit formation. And then as I say, the interference fit generally we do not check very frequently, then we either we require NDT test also, then we do not open it and still we can see what is really happening into the joint, then we will give a success. But there is a possibility you load from the one place and we are getting after 1000 kilometer or maybe say 10,000 kilometer that piece in the other location, and you find phatic wear already occur. So, there is one possibility, and I am just trying to show possibility of the fatal failure or silent failure or maybe silent killer of the materials, that is a phatic wear. What we say the phatic wear happens when the two surfaces move in relation to one another repeatedly at a high frequency, but very simple very small amplitude. As I mentioned here, the amplitude may be from 1 to 300 micrometer, it is very small. Now, repetitive motion may remove the surface material and the two surfaces in a contact, and there is some sort of movement with a 1 micron, and because of the continuous contact and uncontact or the loading unloading is like a fatigue, but there will be possibility of the surface the material removal from that surface, a localized surface, and then it will finally lead to the surface wear, surface degradation. But particles or debris will not be able to open up, will not be able to expose to us or maybe the person who is operating is, what is the reason? Because of this debris particle they are caught between the two surfaces, and not allowing that the two surfaces remain in contact in such a manner particle does not come out and you are not able to see the particle. So, that is why either we can if you want to observe it, we can do for the non-destructive testing, then we can observe this particle, otherwise we will not be able to detect unless there is some failure of that joint. It occurs in most of the mechanical assemblies, at least I have come across a number of press fit, rivet and bolt joint, even though we know the bolt joints can be open up. And if you have been using bolt joint or even a cycle, whenever you open, you will find some sort of a debris there. It can be black color debris, it can be the brown color debris will be there. Even in the aluminum joints, you will find some sort of black color debris will be there. So, this is where the phatic wear is more common, because we assume that they are joints, they are not moving related to each other, but in reality these joints are moving related to each other, only the amplitude is unnoticeable, as it can be very small, we are not able to really see from naked eyes. And then also we mentioned in the ropes, we have seen rolling element bearings, we have seen this kind of failures will occur. Now, we can say also phatic wear contributes to the early phatic failure. Small the pits are formed and finally leading to the major phatic failure. So, phatic is leading to the phatic failure and phatic conditions are leading to the phatic wear. So, they are related to each other, and as I say that in the amplitude can be 1 micron on the around 1 micron, and then if you want sliding motion, maybe say because we are not intending, we do not want any sliding, even in this situation if we try to provide a lubrication, it does not help. That is a real problem. Even lubrication cannot reduce the phatic wear in this situation. We continue the fretting, we say that now let us see the two surfaces in a contact, one surface 2, they are in a contact. When they are in a contact, what will happen? Pressure, when the load is applied, pressure will be maximum somewhere at the center, and then we can find this kind of pressure profile. Pressure is a maximum, but now we are trying to move one surface, not intending, but because of the vibration, because of there is some motion is happening one way or another way, there is a tangential motion. You can see the tangential motion where the stress will be almost 0 at the center, while at the lower outside, or maybe say where there is a joint has been formed, there will be maximum. So, we were saying where the compressive stress is maximum, tangential stress is almost minimum. Wherever there is a lesser compressive stress or almost 0 compressive stress, tangential motion is very high. So, this is a typical situation, and that is why we say the contact pressure in a Hertzian contact, this is a Hertzian contact, the two surfaces are connected to each other and they are subjected to elastic deformation to some extent because of the load, decreases from its peak in a contact to the 0 at the edge. So, this is what we say contact stress or contact pressure, and that has been shown here. This is the contact pressure or contact stress have been shown that it will be maximum at the center and at the end it will be 0, or edges it will be 0 here, these are the edges, this is the center, and you say that there is 0 at the edges and then maximum at the peak at the contact center. And then if you are thinking of there is some sort of frictional energy loss because of this contact and because of there is some sort of vibration, and naturally if the energy is provided to the joint, it has to be dissipated, it has to move to some other place. So, that is what we say friction, and the motion is happening into the axial direction or other direction. In the situation we can assume a uniform tensile stress. However, in this situation we have shown it is not a uniform, and it is somewhere maximum at the outside and minimum at the center. There is a possibility, however, we can assume anything, this is a real situation we have mentioned. And then in this situation we can find out the local coefficient of friction. If where in the compressive stress is a maximum at the center and tangential stress is a minimum at the center, naturally coefficient of friction in this situation we say coefficient of friction at the center is almost 0. Now, coming to the outside where there is a maximum tensile stress and the minimum compressive stress, then in this situation at the edge, this is at the center and this is the edge, will be very high, even at more than 1, or you can say it can be more than 1 also. However, in the what we have written here, the friction coefficient increases from highest point, the highest point will occur at the contact periphery. Few people and few literature, they can say coefficient of friction can be infinity, because there is no possibility of the wear debris coming out from there, right. However, we are not mentioning infinity, we say there will be some sort of slip, and then the slip will occur when the tangential stress becomes greater than friction stress. If there is a friction stress and then there is a tangential stress, which is the applied load is going to increase, then there will be slip formation, otherwise there will not be slip. In short, in this contact region, there is a tensile stress, there is a friction energy and there is a compressive stress, and complete thing will be happening in this region only. Generally, when the wear at the center will not occur that much, or even will not occur in this domain. It will occur mostly in this domain, peripheral domain, where the wear particles try to skip, but still they remain intact there, and then tangential stress is very high there compared to the center. That is why there is a relative sliding, there is a possibility of relative sliding, and then if there is a relative sliding, the wear will occur. We will continue on the fatigue. We say that fatigue is happens in mostly in interference fit, and that is what we have shown here. This is the rivet joint, you are able to see this is the rivet joint, and then rivet joint, there is a interface somewhere here, contact interface will be here, contact interface will be here, contact interface will be here. So, there are many locations for the contact interface and possibility of fatigue wear, and then it is impossible to avoid the 1 micron motion. If there is a one assembly of the and this is a riveted assembly, it is almost impossible, we can say, oh, we cannot avoid the 1 micron motion, it's a vibration will occur from outside environment. Same thing has been shown in the nut and bolt connection, and where whenever we open up the nut from a bolt, we will be finding the some sort of a debris at junction in this surface to this surface, there will be some sort of a debris. It can be black color debris, it can be red color debris, this will occur. And the same thing has been presented here. If the contact occurs only in this surface, it is a cylindrical surface, then in this domain the wear will occur, and maximum wear will occur at the edges compared to the center, which was shown in the previous slide. And then again we were saying, as I say that it is not possible to avoid it. However, we are saying the minus light does not cause a concern for the several cycles. Failure is a continue, and we are not able to see that failure, that is why we do not worry that much, but failure will be there. However, finally, when you open up this connection or nut and bolt connection, we will be able to find out the wear scars, wear debris, they are intact. And then as the debris is getting removed from a surface, after that clearance will increase. If the clearance increases, that will lead more and more what we say that amplitude. So, initially if it was a 1 micron, it will lead next time fixing it will give 5 micron, next time it will give 50 micron, next time it will give 100 micron. So, finally it will go for the complete failure, and this is what the fatigue wear does. But we say that continuously the wear will occur, it is not getting stopped because of the motion. Now, we say the wear debris, why we are not able to see, because wear debris becomes entrapped within the sliding interface due to limited sliding amplitude in relation to the size of the sliding contact. So, sliding contact is a big patch, and then it is happening a perfect sealing outside, and maybe whatever the debris which are getting generated here, they are not able to come out because they remain intact and inside this circle. And then when you open up, then only the lot of debris will come out from the space. On damaging surface, a layer of the one debris accumulates over time, because these particles are not able to come out, they will keep getting accumulated. In fact, initially the few particle, after that even this particle will act as a abrasive material, it will cause a more and more failure and continue depending on the formation of the new debris and how sensitive are those debris to further increase the wear rate. So, naturally that will be coming will depends. However, the new debris itself acts as the lubricant, then quite possible that the wear rate will come down significantly. Wear will remain there, will be there, but quite possible the new debris are providing some sort of slow dying mechanism instead of enhanced mechanism, instead of increasing mechanism. So, what we are saying, the phatic wear accelerate the mechanical fatigue by causing surface cracks, which will happen mostly the surface crack will form in a phatic wear, it will not be subsurface. To grow around the wear scars propagates and eventually fail. Now, this is the next slide which we are trying to show growth of the phatic wear, but we are saying the initial one is a stick phase. We are saying that the riveted joint remains in a connection, and but still there is a wear rate, and these all are the 10 to minus 16, 10 to minus 15, 10 to minus 14. So, we say that there is a phase 1, phase 2, phase 3 and phase 4, right. So, we can say that even with a good construction, good design, load variation and thermal expansion cannot be caught. We cannot minimize to 0, it will be continuing, and then based on the phatic wear will occur. Phatic wear can be divided, subdivided in 4 steps, and the first one is a stick phase. What is the assumption? The joint surfaces are in a close contact and almost negligible or 0 relative movement, and that is why there is a joint. However, because we are forcing and we are connecting the 2 surfaces, naturally there will be high compressive load which will deform the surface to some extent, and there will be some sort of a contact stresses, and because of the very high contact stresses there is a possibility of some sort of micro crack formation, there is some possibility of micro crack formation. Now, when the second stage, that is a mixed stick and slip, that is what we are saying. Now, when the joint is subjected to additional external load, we have joint with a lot of compressive force, which is giving some sort of a few micron size cracks, and then it is subjected to the vibration or a change in the load condition. This mixed stick slip in the phase will start or begin. Joint surface move slightly during this phase, but even though there is a movement, there is a sliding, but there is a tremendously high contact pressure or contact stress. So, the surface remain in a almost same position, it is not visibly moving. So, if I say the distance, maybe say 1 to some T1 micron movement, and then the second we are saying that maybe something like a 10 to 12 micron, which is again invisible to us, we will not be able to notice it. That is a stage 2 or phase 2. Now, coming to the gross slip phase, where the micron size movement we will be able to notice, and it is a repetitive in nature, dynamic in nature and cyclic in nature, we can really notice it, and that is why we are using the word the gross slide motion or slide phase, because in this situation already whatever the intact or closed condition they have loosened to some extent, and then there is a relative motion starting. So, if external stresses the vibration continue to rise, increase, in the situation the one surface related to the other surface will slide, will move, and then what will happen, in the formation of the wear debris will occur. Quite possible the wear debris were there earlier, were formed, but now visibly we will be able to see, and there is a possibility that wear debris are coming out of the joint also. Another thing is that maybe there was some sort of oxide layer that will also get ruptured, which is earlier oxide layer was providing some sort of lubrication, that also get ruptured. So, this debris and oxide layer will come out, and then quite possibly they will act as a abrasive material, and then it may further damage the joint surface. So, that is what the wear rate is increasing. Wear rate is almost negligible, 10⁻⁻15, moving to the 10⁻⁻15, and then finally it is coming to 10⁻⁻14. And finally, after that it is really the reciprocating sliding motion. We say now phatic has done as a damage, we require some other mechanisms to explain this phase, and that is why we are saying that in the fourth phase joint surface moves significantly, causing a severe damage of the material or the failure of material, and now it has generated a number of surface that will propagate with other mechanism, and then finally failure of the joint will occur. Now, what will be result of this kind of a mechanism or 4-stage process which we have discussed? We say that there is a possibility of the wear debris which is generated, which has a much lower dimension, maybe initially is 0.01 to 0.1 micron. So, it is a nanometer level, and then there is a possibility of the joint loosening, it is causing a increase of vibration, and that is going to lead the accelerated wear. Now, I am going to show the two the patches A and B. You can see in A there is a pit formation, and it has happened because of the joint, and then it is a 20 micron level, that means this will be around 100 micron as such. So, this 100 micron which was earlier as a joint, when we open a connection, then we find this kind of pits formation there. And in this case particularly you can see the increased surface roughness. Now, this surface roughness has gone very bad, it is almost a very rough surface, which we will not be able to use, or we should not use in our regular cases, and there is a micro pit, increase in surface roughness, and this all causes a reduction in a fatigue strength. So, that is why the phatic wear leading finally to the fatigue failure. Fatigue is causing some sort of a loss of the material, it is causing a surface damage, and that damaged surface finally will fail under the fatigue loading. And now, how do I identify the phatic wear or not? See, often the matting surface they lose the color, they become they change the color as such. Now, we have observed aluminum oxide as a black color aluminum oxide. In case of iron oxide, we have seen that the 3 different forms. We say the ferrous oxide does not occur very often, however, there is a black magnetite oxide which is a black in color. It is very soft also, that is why we say that this kind of wear will be helpful to provide a solid lubricant, and that is why it is a preferable. However, in the situation when it will occur, when there is no moisture, if there is no moisture we will be able to see Fe3O4. However, if there is a moisture, and then there will be some sort of the rust and corrosion, and the rust and corrosion, the wear debris are generally harder compared to the earlier one, the black magnetite oxide, and this hard and abrasive particle will cause a more severe damage. So, quite possible phatic wear leading to the abrasive wear if there are hard particle and oxide particles like iron oxide, in this case Fe2O3. And then we have observed also there are few metals like a titanium or alloys, they are very susceptible to the phatic damage, and we should not be using in this kind of joint connections, and then we should be using the better connection. If you want more and more study on this, because we have understood that many bridges failure have occurred because of the start phase is a phatic wear, and after phatic wear other wear mechanism dominate, and this is more like a silent killer. It really the damage to significant level, and after that we need to do a regular maintenance or reconditioning of the surface, then only the things will work properly. And as I mentioned, and how do you reduce a phatic wear? As I say, if the moisture can be reduced, and then we can provide this kind of lubricant, it will really minimize, it will really allow us or we say that regular maintenance is a good solution compared to any other solution. Now, we are moving to the next wear, that is called melting wear, and it is also very rare, reason being the temperature has to go very high, and mostly we design a component or system or we select the materials in a manner the temperature should not go on a higher side. But there are cases, and we have observed also, and one case has been shown here when we doing the 4-ball test, and then we were trying to find out the lubricant, we could find the melting wear on the surface. The ball is with this is the wear score on the ball, and then the melting has occurred, and if you leave for some the time, this molten metal will get again solidified, but you can see there are cracks formation, and now if you go for the sliding condition, this cracks will generate a wear debris, or maybe the complete fragment which has been there are number of cracks in between, fragment will come out as a wear debris. So, this has been what I have shown, that the ball failure in a 4-ball tester. 4-ball tester is one of the tribometer, we will be discussing when we go with testing machines or the discussion of testing machine, and then we apply extreme stress to find out whether lubricant is working or not, and that is what the example we have shown this one. And as I mentioned that in this we go through extreme pressure, and then because extreme pressure there is a, and then if we do not have a sufficient good lubricant available, it will cause a frictional heat, and because of excess or high frictional heat, there will be a melting or softening of the metals, and while the melting, and then or maybe say the softening will cause a flow of the materials also. In this situation, we say that where debris accumulates in a rupture form, you are able to see here there are number of ruptures or number of cracks on that, and then if you subject further this kind of the component under sliding condition or extreme relative speed, then again the failure of the lot of wear debris will come out of the surface in this situation. So, we can say that due to frictional heating and heavy loads, there will be a localized heat generation and a high speed sliding between the contacts. So, heavy load is a 1, high speed sliding is a 1, this makes surface damage sufficient, and then in this situation because of the high sliding and then high load, there will be frictional heating, and the frictional heating between the contacts, and if we are not able to dissipate the heat easily, then there will be temperature rise, and this temperature rise, if it goes beyond a melting point of the material, naturally a molten layer will be formed, will be there, and then this layer will be known as a melting wear. Wear is removed immediately, then there is no problem, but otherwise if the layer is not removed immediately, then it will solidify. Further wear condition will separate that material as a wear debris, and finally it will come out in the form of the droplet and can be irregular complex also. However, one more important point is that whenever there is a melting happening, what will happen? There will be atmospheric oxygen present. If atmospheric oxygen is present, then quite possible the molten layer will act with oxygen and make a oxide layer. After that, it is going to really change the material characteristics and the material behavior also. But melting will be there, formation of oxide, whether that oxide is a beneficial side or worse side, that will depend on material and its of oxide formation. So, if we try to sketch what is a molting wear, we can see there is a surface 2, it is under high load condition, it is leaving some sort of red material on a other surface, and then if the layer is a thicker one, maybe say few micron, quite possible, and that solidification there will be some sort of a crack formation in this layer also. So, that is why we can say the frictional temperature rise is proportional, particularly in this case depends how fast we are moving the materials, and then it depends on the velocity of the material, and that is why if the frictional temperature will be more if the relative velocity is very high, and then there is a mathematical relation has been given, the temperature depends on the square root of sliding velocity that has been mentioned here, and it also depends on the frictional the coefficient of friction. higher the coefficient of friction, naturally this temperature rise will be on the higher side, lesser the coefficient of friction, temperature rise will be lesser, and then sliding speed, also very high sliding speed, temperature rise will be on higher side, lesser sliding speed coefficient, and then the temperature rise will be on a lesser side. So, these are the some the elementary knowledge related to melting wear, and as I mentioned, it is depending on the localized heat. We do not have that much energy that which is getting sprayed over the complete surface, it is just localized. Heating will happen, molten layer will come and then solidify immediately, it will not spray complete surface. And then frictional heating and the substantial load creates a molten layer between two surfaces. What we are saying, the melting wear is caused by heat, and it is just a few micrometer thick, it is not really the complete material is flowing on the other surface. It is just localized phenomena, melting, solidification, and then solidified layers get converted to the wear debris. But finally, it is coming out of the surface. So, that is why there is a material loss, that is why there is a wear loss. So, what we say that when molten layer interact with the atmospheric oxygen, there will be a formation of oxide layer. This oxide may affect subsequent wear characteristics and friction characteristics. It may be helpful, it may be harmful, depending on the behavior of that. Now, let me introduce a new concept which has been popularized or used in literature almost for the 3 decades, and that concept is a wear map. What is a wear map? Generally, the wear maps are made for some sort of a material which is the most commonly used, and few authors they have given several such wear maps for the material. So, I am just showing a steel material, and then they use a pin on disc configuration to find out this kind of a map, and then they are also showing the ultra mild wear domain, right. And in this case, vertical line, this is the normalized pressure and this is the normalized velocity has been given in this form. And in this we are able to see that as the pressure is increasing, wear rate is continuously increasing. As the sliding speed is increasing, wear rate is also increasing. However, there is a ultra mild some domain, if you are able to operate in this domain, that will get the best results. If we are not able to operate in this domain, then either load is on a higher side, naturally there will be some sort of plastic dominated wear, and then after that there will be some sort of oxidational wear, and coming to the high speed side, there will be oxidational wear. Here we are using the word mild, here we are using the severe. As the speed is increasing, the material will experience a severe oxidational wear, and what we are talking of the melting wear, which comes in this region. That melting region itself comes as a severe wear. Melting region or melting wear is a severe wear phenomena, and if we do not take appropriate action, finally it will be seizure. The seizure is very high, that means we are trying to provide a relative motion to two surfaces, and surfaces are not going to move, on complete energy is getting converted to heat, and that heat is further causing a more and more failure. So, that is why we should avoid this kind of phenomena. Even we should avoid the melting wear, and then we should choose the right material. We try to come up with the ultra mild region, and this kind of wear maps are popular and available in literature for the several materials. It will provide a good number and a good help to the academic faculty or students who can go through it and can select the material. Again, we can get a suitable material from this kind of maps, but we cannot rely completely on that. We need to test again those material pairs in a real situation, or we may say the simulated situation. We need to perform again the way they have done the test on the piston on disc machine. We can do a piston on a disc machine, we can do on a 4-ball tester, we can do on some other tribometer, but we need to confirm. Reason being, from one domain to other domain, the wear coefficients will keep changing. It may be 10 times, it can be maybe say more than that also. So, everywhere the situation will be somewhat different, operating condition will be different, environmental condition will be different. So, we can provide we can get some sort of hint from existing literature, So, finally, we need to perform experiment to get a right results. So, what are the critical points about this wear? We say it highlights critical wear mechanisms. What is why we are using what? Because here we are able to control, that means all operator are able to control pressure and velocity, and they are only the two, in this case pressure and velocity both we are able to control. And then what we say that then in this case there are field boundaries, these are the some sort of boundaries have been shown here, and then we are able to really calculate those things. How? Now, suppose there is a mild oxidational wear this side, and then there is a severe oxidational wear this side, and then if we try to use wear equation for this mild oxidational wear and severe oxidational wear, naturally this kind of the boundaries will then we can find out this kind of boundaries in this. There will be some sort of variation and this boundaries can be obtained. Let us take example, if we want to have a wear equation for the severe oxidational wear and the mild wear, we equate and then try to solve, quite possible we will able to find this boundary. Similarly, if we have a wear equation for the mild wear and seizure and then we solve it, then we were able to find out this boundary. So, this is what we say, this is the easier one, this is also easier, where equations are there. Again, one complete wear equation, relying complete wear equation will be little difficult. So, that is why you are able to see some sort of, instead of just thin line, there is a thick line. So, there is a variation will be there, it is not we will get exactly same results. Another one, there are contours, this you can see here the contour 10⁻⁻11, 10⁻⁻10, 10⁻⁻9, -8, and that is where we say the wear rate. So, again this is not a velocity, it is a wear rate, and then here interesting thing is that this will provide summation of all kind of wear mechanism. If there is abrasive wear, adhesive wear, fatigue wear, fretic wear, all together, what will be the final wear? And that is the this constant is going to provide in this manner. That means, all the wear equation finally should come in a similar kind of form, only there should be change in a wear coefficient, and that is why we try to introduce equation in a manner where the wear equation is changing and giving a results to us. Now, another point comes oxidational, where we are talking, sometimes we say the formation of oxide occurs under sliding, deform, and then this oxidation layer also will be removed, and the nascent surface will come, or the virgin surface will be exposed, but again it will get a chance to get oxidized. So, oxidation formation and removal will be a continuous phenomena. So, that is why we say that to govern that, three elements that govern the oxide layer thickness are rupture time, how much time is required to rupture the oxide layer, then how much time is really required to re-oxidize that layer, and finally, and then the formation rate, what is the formation rate. So, if there is a balance, then oxide layer will remain there. Quite possible, if there is no balance, oxide layer may grow, or complete oxide layer will be getting removed. So, these are the situations we need to solve, and this is a complete thing comes from a wear map. And then what we can say, what we have understood from wear map or something like a wear maps or graphical representation to depict the wear behavior of materials under certain condition. That means, it can be a one typical material, and we can really find out under different condition how it will behave. These maps help us to understand and focus a wear mechanism, as well as determine optimal operating condition. What will be the optimal operating condition to minimize the wear, to reduce the wear? We can spot patterns and the key operating situation where the wear is most severe. We want to avoid a severe wear, we need to come out what will be the critical factors which should not happen at all in even the worst to worst situation. So, those factor patterns can be spotted using the wear maps. Wear map can assist in the selection of appropriate materials, because if we have a 15 maps or 20 maps and we are connecting, and then we are almost in a similar situation, which material is going to go ahead with better results. Again, only for one condition may not be right thing, but we need to see what will be the fluctuation in wear condition or operating conditions, and then choose a material based on that. So, we are saying the wear map can assist in the selection of appropriate material, optimization of the design parameters are also possible in this map, and the development of method to elevate if we are thinking about the lubricant, if we are thinking about the coating, it will allow us to think in that direction and give a right direction or right suggestion to go for the innovation or invention. So, in short, we can say MAP aids in the design of wear resistant components and the systems. So, they are very important, they are very useful. Now, I am just showing one step ahead of that. In wear MAP, we introduce one concept called a seizure, and then what we say, the severe wear to seizure is important. Why we are using the word the seizure is that in the earlier we were talking about wear debris in a micron, but you can see here this is a 254 micron, the very big wear debris which is coming out. Even these scratches or lines or deeper is almost 127 microns. So, these are the deep one, and these are the further deeper, and then the depth is on much higher side. I shown also the two examples. In this case is a complete seizure. Now, because of the high temperature as the melting wear, that balls are getting connected, they are making adhesive bond with inner ring itself, and separating this it will be task. It will not come out easily. So, we need to do really a manual separation of these kind of rollers, and that is why we say that what has been shown, roller bearing, inner ring and rollers, and then after seizure generally do not these components will not get separated their own, and then to separate we require a force to separate, and then after separation you will find out they are completely useless, it cannot be reused. You can do a reconditioning, but again it will require some time and it cannot be getting reassembled in a similar manner. So, this is important to understand, and you cannot operate also after disassembling, again refitting and operating it. Reason being, already there is a huge wear, almost 50 to 100 micron, then the rollers have been worn out, and if you use it, clearance will increase. And rolling element bearing, we find a very low clearance, maybe tune up 10 to 50 micron, and there is already more than 50 micron the surface has been removed. Naturally, it will cause overall more than 100 micron clearance. So, earlier some clearance and more 100 micron clearance, that will cause a huge vibration, and then very low stiffness, and then it will cause a lot of noise. So, bearing will turn out to be totally useless, and then we cannot use this. So, that is why we say the materials has been lost from a surface of the roller bearing and then cannot be used. So, that is why we say that the severe wear, severe adhesive wear, which is we have been showing, we have been demonstrating it or depicting it as a load increases, moderate wear change, moderate wear rate changes to abruptly wear rate, and then this wear rate increases several times. If wear rate was initially ultra mild, then maybe the mild, then maybe the moderate, and then the severe, but this is not a linear increase. There will be jump every time, ultra mild to the mild there will be some sort of significant change, the mild to moderate there will be a much significant change, moderate wear to severe wear will be much significant change. So, what we say, increased load distort a surface to the point where oxide film and the deposit will not occur at all, and then the oxide film will fail completely, it will reveal the fresh metal, and then this fresh metal, if does not have a sufficient time to rebuild oxide layer, quite possible will cause this kind of adhesion, and that will cause a failure. So, here the melting is causing adhesion, melting wear is causing adhesion, and that is what we need to notice, that how the wear mechanisms are related to each other, and that is why we say in this slide that after all number of wear mechanism will work together, and then we will be interested, we need to be interested in a wear coefficient, minimize the wear coefficient and get a good results. So, what we have understood in a seizure is something like a seizure is to bind or fasten together. After a seizure, tribopair lose its complete utility and cannot be reused, cannot be employed back. Some people say the reconditioning it is possible, but again we need to keep a very close conditions or close operating condition in this situation. Relative sliding motion between two contacting solid generally results in the loss of the machine mechanical energy, and if there is a loss of the mechanical energy due to friction, naturally this energy need to be dissipated, and that this energy, if you do not have a sufficient dissipation mechanism, it will build on the temperature and the temperature will increase. An increase in a temperature will cause a melting wear, and increase in the melting wear will, if it is not controlled, it will cause a shear. So, they are related to each other, and then there is a major issue. And then if you want to avoid this kind of melting wear or shear, we need to think about high thermal conductivity of the material. So, whatever the temperature comes, immediately there is a good thermal conductivity, the heat is dissipated. Second, if we are not able to dissipate immediately, think about how to reduce the friction, how to introduce a lubricant in this situation. If it is not happening in proper way, then we think about how to provide a coating which can really reduce the friction and then reduce the temperature. If it is again not possible, we need to think about a maintenance, how to go ahead with a regular maintenance. Many times, even after doing all this, still the failure occurs, still the melting wear occurs, still the shear occurs. Then we need to see whether assembly which have been assembled in a manner, is there any misalignment, because misalignment has caused major problems, and often we are not able to notice. Even 0.1 degree misalignment can increase the temperature by 5 degree. If I go ahead with a slightly more, then temperature rise can go with a 180 degree also. So, many times the misalignments really give a more problem compared to the other aspects. So, we need to see all 5 criteria if we want a durable, reliable results from a component. Now, let me come up with some sort of quantification of the melting wear. What we say that here we have been talking again and again on the temperature. It can be a flash temperature, it can be bulk temperature, and melting point occurs and then when the bulk temperature reaches to the melting point. Even though we are saying instantaneous, there is a flash temperature, there is a possibility of the melting as instantaneous. However, the melting wear is a more dominant, whether the bulk temperature is a more than melting temperature. So, here we are trying to show there is a pin and the disc arrangement, and the pin and disc, some sort of a geometry which are coming in a contact, and then there is a tangential speed on this, and then there is a heat which is getting generated at the interface, and then because of that there will be temperature rise, that will be bulk temperature. So, we can equate the how much friction energy has been generated and how the heat is getting dissipated. So, we compare friction energy with the heat flux and the rearrange equation, we can find out the bulk temperature Tb in terms of environment temperature or atmospheric temperature or temperature sink, that is what has been mentioned here. With that some sort of fraction, not necessarily 100% friction energy is going only to the temperature increase. If there are some other mechanism where the some fraction is going, so alpha is not equal to 1, it can be 0.8, can be 0.9. However, this is the coefficient of friction, there is a friction for then this is applied load, there is a tangential speed, and this is the area, and that can be equated. Here we are saying this is a conductivity coefficient, it is related to thermal conductivity of surface, and then as I mentioned, alpha it is just a fraction of the heat flow which is going to increase the temperature rise. However, if you think about the flash temperature, which is more important in my thinking, because that will naturally give a higher temperature compared to the bulk temperature. If we are able to keep a check on the flash temperature, then more or less bulk temperature will be under control. And then if we can think about the asperity level also, what is the asperities, and then what will be the temperature rise at there. And if the asperity level, the temperature rises on higher side, there is a possibility of the seizure happening there, melting here, we are happening here. That means initiation of the most of the problems are happening at the asperity level. So, in this situation it will turn out to be uncontrollable. If you are able to keep a control of the earlier stage, it will be really better results, it will provide a better results to us. Now, just to highlight this, I will just take one example on the gear pair, and what we have covered in previous slide is that the rate of heat generation per unit area, that is a coefficient of friction, relative slide, and then contact stress, which is what we say the gear pair generally go through the contact stresses. And this sigma d distribution can be found Hertzian formulas, and that is we are obtaining this kind of formula which is related to Hertzian contact relation, and that this is the empirical formula. We are not going in the depth, because with there in the depth we need to really solve the thermal equation, we need to solve complete elastic equation, and then it will take a much longer time. So, instead of that well known empirical formula, I am just trying to bring to this class. You say that this is the flush temperature Tf, it depends on the coefficient of friction, it depends on the relative velocity, it depends on the applied load, the normal load in this situation. It also depends on the Young's modulus, what we call effective Young's modulus. It depends on the effective radius of curvature, that has been also mentioned here, and this is the face width, how much is the depth of the gear, that is the face width gear, and then this is what we are using the beta 1 and beta 2, and beta is being represented as the coefficient of thermal conduct. So, every author has a different terminology, and I am using the word of the Bartz. Bartz has a famous book on the gears, and I am just picked up this formula from Bartz book, and this is a coefficient of thermal contact is beta can be given as a thermal conduction, specific heat and density, that the lambda, c and rho. This is what we have been utilizing in this kind of material 1 and material 2. If any of the material 2 beta is a lesser, naturally temperature will be on the higher side. If beta value on the higher side, temperature will be lesser. So, we should choose a high value of the beta whenever we go through the material selection. And as I say, if the effective Young's modulus is this side, and effective radius of curvature or the effective radius has been given on this relation. Now, here what we are using Wn, and we know that in a gear Wn can be calculated from a torque, applied torque is a T, and if you know the pitch radius, I can find out the Wt as such, and then Wt can be given in terms of the normal load on the gear pair. The Wt can be given as a pressure angle, the cos phi, pressure angle phi is a pressure angle, and then Wr, which is the radial force, can be given as a Wn into sin phi, the sign of the pressure angle. So, this is a more important. Once we calculate this, we can substitute all this value in this relation, and we can find out what will be the flush temperature. So, we require some data, and then this is another formula, slightly modified formula has been given by Bartz, and then says here that is what is the relative speed of the pinion and the gear, and this is what we are again using the beta the conductance related. This is applied load Wn, and this is the face width of this gear. This is the module, number of teeth, effective Young's modulus, and this factor Fz, that has been given by author in this manner. We say that as a number of teeth are increasing, stresses level will come down, and then if stress is coming down, the coefficient will come down. That means, if this is the coefficient here is 0.813, the number of the teeth is 17, if I increase to the 100, this 0.813 will turn out to be 0.124. That means, a 6 time can be reduction will happen. That means, if the temperature the 17 teeth is something like 100, quite possible if a number of teeth are increased to the 100, quite possible that it will affected this flush temperature will turn out to be only 16-17 degree. So, there is also possibility of design change whenever we think. Now, in this the author has given a comparison between the nylon and nylon pair. If I choose a gear material between a nylon and nylon, or a nylon and steel. So, these are the two pairs they wanted to compare, and I am just trying to show the results of that. Number of teeth they selected 17, module 3, face width 30 mm, and angular speed is a 150 radian per second, and then power transmission is around 850 watt. This is the same formula which was highlighted in previous slide, and the coefficient of thermal contact beta has been given here. So, they have provided a beta value for nylon versus nylon. This is the value 0.417 10 to 6, and nylon versus steel, which naturally this has increased significantly. Here is almost this is a 360 times compared to this, or maybe more than that, almost 400 times. However, the coefficient of friction in both the cases is same. Many times people say the coefficient of friction is very important. He has kept the coefficient of friction same. Another one is the Young's modulus is almost double in this case. So, what he calculated in nylon versus nylon, TF will turn out to be 161 degree, while TF and the same operating condition in nylon is the one material is same, but other material is steel, and this TF will be 9.5 degree. How it has happened? I will just show you some calculation, and then so the simple program has been written to find out tangential force, normal force, contact the flush temperature. This is pitch radius and the torque which has been given, and one case we have a given beta value, particularly nylon versus nylon, as a 0.417 10⁶, that is the 417,000, and then we also have kept absurd the same, E prime same, almost the same. Yeah, E prime is maybe the nylon is a half compared to the nylon versus steel. So, these two parameters, so one this and this has been changed, and we find the calculation that TF in case of the nylon versus nylon is a 160.75, it is almost a 161, while in case of the steel versus steel it turns out to be a 9.2 degree. So, there is a huge difference by just changing the material pair. You change a material pair and you get a better results. So, this is important when we try to calculate. Again, this is a just introductory part, and then we are trying to say that this will happen. To really test and get the same result, we need to do a experimental test and to validate that. Now, we will be covering this the surface fracture surface degradation is next lecture, and then we will try to we have tried to cover the wear related failure surface degradation to first 6 lecture. We will move to the lecture 7, fracture surface degradation level 7th, and then as I say abrasion the diffusive wear, which we just highlighted into this one lecture. Thank you.